Hey everybody, welcome to Houdini Hangout. It is Saturday the 21st of January, and we're doing the last day of our Joy of Vex series. We're going to be covering days 19 and 20 today. Some interesting stuff to get through here, kind of in the home stretch of the content. Just some really interesting functions to get into. Be talking a little bit about prim UV and XYZ dist, and then talking about point clouds in the last day, and definitely some kind of exotic use cases for these things, but also there's some practical uses as well. So these are things that are always good to kind of have in your back pocket, ready to go, and if something comes up, then hopefully you'll have the just the ability to use one of these to solve a problem at some point. But anyways, let's kind of dive into everything here. Just a couple of quick things to just note. If you want a link to our Discord server, it's on HoudiniHangout.com. You can go there, get an invite, and join up from that. And in order to follow along with what we're doing today, here is a link to day 19 of the Joy of Vex. You can get to all of the different sections of their website there. Oh, looks like I have a connection issue here. Interesting. Well, maybe not. Hold on. Interesting. Might have to do something there. Not sure what that's going to be. But anyways, let me just double check to make sure that we're getting our chat over here. We might not be. No, it doesn't look like it. Interesting. Give me 1 second, just making sure everything is working here. Well, that's a bummer. Sorry about that. I updated something on my Twitch, and for some reason the chat is not connecting over there. So if you need the links to this, I'll make sure that once I get all these things cleaned up, that they'll be in the description on YouTube. So if you need to get to them, but basically we're at the cgwiki. You could just probably search Joy of Vex cgwiki and be able to find your way there pretty easily. Actually, you know what? I can just throw this in the chat over there. Actually, sorry. Let me do that. There you go. There's the link over on the over on Twitch as well. Let me just make sure yep, there we go. Cool. Great. Sorry for the little bit of issue there. I don't know what's up with that, but I will try to get that sorted for the future. Anyways, what I'm going to do is actually going to need to watch two chats here. So let me get that sorted here. Okay. Cool. Now I've got two chats that I can keep an eye on. Sorry about that, folks. We will be ready to roll now. Okay, great. So anyways, we have that link there. That's where you can go to find the Joy of Vex. And we're going to also, again, HoudiniHangout.com links to the site. If you guys have any thoughts or questions or anything like that that you have during the stream, please drop them into the chat. Be happy to take a look at whatever questions you might have, and we'll make sure we can make those corrections kind of as we go along. Don't want anybody getting lost or anything like that. And huge thanks to anybody that might be watching today that normally can't maybe watch or whatever. Just because of time stuff. Glad to have you guys here live today. And hopefully we'll be able to, just engage a little bit and have a good time here. So excuse me. Sorry. All right. Well, anyways, too much. Hey, Kazulo. Wow, that's I probably am missing whatever however to refer to you, but hello, welcome to the stream today. All right, let's jump in and actually do some Houdini, and we'll go from there. Cool. All right, so here we are, day 19 of the Joy of Vex. Hey, Crossfader, how's it going? Just as a little note too, you won't see the little chat up here because for some reason my Twitch isn't connected to the chat. So anyways, just a little note. But hello, hi Crossfader, nice to have you. All right, so the first function we're going to be talking about is prim UV. And the idea we're going to talk first about is how to stick things to geometry, right? How to kind of keep a point stuck in position on a geometry. There's some ways to do that at object level with connecting objects between each other, but this is going to be a little bit more fine control of being able to kind of go in and tweak these connections, right? So in order to properly stick stuff, we're going to use the prim UV function. So what this is going to do is basically we're going to give it a primitive ID and a UV coordinate, and then that's going to return some attribute from that location on the primitive, right? So first let's set it up, and then we'll look at this code here. So let's first set up this little network here. It's a little hard to see, but hopefully you can understand what we're about to do here. So, all right, we're going to need the rubber toy. We're going to need a grid. We're going to grab an add sop here. Actually, I'm going to make this a little bigger just so you guys can kind of see what's going on here. Okay, so we've got our add sop. We've got one point in there. We're going to do a point wrangle here. We're going to stick the grid into the second slot, not the third. And then we are going to take the rubber toy. We're going to do a transform there on that. We're going to use a copy to points like so. I'm just going to shift click these two, and then that when we connect it there, it's going to connect them all in. And I'm going to do the same thing to make a merge. So I'm going to click this, shift click this, and then alt click here. And that's going to give us a merge node. Then we can do a normal at the end here. I believe that's just to clean up the visualization in the viewport. And so we've got something going on here, right? So we have this point right here. If we hit enter while we're in that, looking at that node, we can see that we're copying. Yeah, little network, little tips there, right? Yeah, shift click is really nice. Yeah, you can wire in multiple ports if you shift click a couple of them. So like if you're doing like vellum stuff, for example, like if you have a vellum constraints like this, and you have another one here like this, you can just shift click them all and then click on the first one, it connects them all. So nice little UX UI thing, Anyways, yeah, it's a nice little trick. All right. So cool. We've got this network set up the same way as we have here, and let's put this code into our point wrangle here. So we'll just call this JOV day 19. Cool. All right. So what we're going to do, scale this down. We'll maybe just zoom in like this so we can see kind of the node that we're working on. And yeah, so let's first declare a vector UV attribute. I I think that's big enough. I think we'll be able to see that. So vector UV equal to, we're going to set that equal to vector channel, and we're going to name that UV as well. It'll give us a little way to select what UV position we want to use. Then let's set P equal to prim UV. So we're going to select the first incoming geometry, which in this case is our grid. So we're going to select the first input. We're going to look up the position like so, and we are going to give it the 0 point, so just the first point coming in, and we're going to look it up based on the variable UV that we've set earlier. So that's the kind of the UV position we're going to look up. So cool, that's good. Then let's do n equals prim UV again. Oops, sorry, prim UV. It's kind of the same thing. In fact, we could just copy this whole block of code, and just instead of UV, we'll say n. So now we're getting the n and the p from this this position right here on the on this grid. And so let's see what happens here. So we've got this point. Let's just see our grid as such. There we can see our point. I've made the points a bit bigger, so hopefully you should be able to see it. Great, so let's just create this parameter. And so as we change this around, we'll see that it moves back and forth. The one thing that we're going to do is change this to 2 by 2, right? So now everything is kind of hopefully making sense. We've got this. Let's look at it down here. Actually, we can see that we have. Oh, is that not copying for some reason? It's weird. Did I go past it? Yes, I did, because that was not liking that. So okay, now we're good. So the reason that those numbers were so high, just as a little example here, let's just template that. So the reason that those numbers were so high was because when I set this to 6, 0.5, instead, if I had this at a 10 by 10 grid, that's only going to be looking in this first primitive. And so we're just going to set this as a 2 by 2 grid so we can just talk about one primitive first. And we're going to kind of clarify essentially tell the node. Okay, so the question is, when you declare those, you essentially tell the node to look at that attribute starting at the first point. You'll see all the preceding points to the end and the attributes associated with them. No, sorry. I think I actually said point, and I should have said that we're looking up the prim 0, not 0.0. And I think I made that mistake there. So when we're declaring these prim UV functions, what we're doing is we're looking at the second incoming geometry, right? So this grid here that's coming in. We're looking at the position. We want to read the position. We want to read the 0 primitive coming in, right? And then we want to use the UV position here. Now, what I can do is, let me actually bring up this help card. And you can just kind of see this maybe a little bit better. What I did is pressed F1, right? So here is the breakdown of that function, right? So we have the first one is whatever geometry we're looking for. Then it's the attribute name we want to look up. Then it's the primitive number we want to look up. And then the UV or UVW value that we want to use there. It's going to be a vector either way. So that's kind of what we're looking up, right, in this case. So cool. So we've got this point here now, and now we can copy our geometry to it like this. I'm going to turn the point visualization off. The reason that this transform is here, just so we can clean this up and rotate it by 90, just like so. Because if you remember, we were talking last time that the z-axis is going to be pointing in the direction of the normal most of the time. So we just want to rotate it 90 so that it's pointing kind of along like that, right? So that's all good. We can now move this around on this grid here. And everything should be working kind of the way we were hoping it would. So it's getting the point position for wherever this, for this one point here. Now, it doesn't matter where it is because it's not looking anything up based on that. We're just explicitly feeding it a UV, right? So now let's animate this grid with a transform stop. So we're going to do a transform here. We're going to take a look at what specifically happens here. So there's our grid. Transform. I'm just going to do the rotate. I'm just going to do this by time times 30. Actually, you know what? I can just do it probably by instead at frame like this. So we'll do that. And then, so that should give us some animation in that axis, right? There we go. And we could maybe do that times 2, for example. And then this, we're just going to do by at time as well. So now we've got just this animating. Oh, I did that by time instead of by frame, which would make more sense. There we go. So now this should kind of be rotating around. And what you're going to see is that this geometry is going to be kind of twisting around as we're going, right? So why is the object that's connected here twisting as we go? Well, the reason is that we haven't really defined that up vector, right? So we've only defined one vector here in this case, and that's normal. So in that case, it's going to try to figure out the best kind of orientation that it can for that object. So in this case, Houdini's kind of just trying its best to create an orientation for that. If you remember, we were talking about quaternions and orients and stuff like that. You need 2 vectors to be able to kind of rigidly lock that in place. Right now, we just have 1, so it's able to kind of spin around on that as it kind of calculates it moving around in these kind of random motions. So that's why that's why little Flippy's kind of twisting like that. So, let's instead of just having him locked in one place, let's actually have him move around kind of in a circular manner here using our Vex code here. So let's clean this up a little bit. We're just going to declare vector UV first. We're not going to be setting it to any distinct any parameter here. We're just going to set it or just declare it first. Then we're gonna kind of independently set each element of this vector. So we're gonna say uv.x, and we're gonna set that equal to the sine of time. I'm actually gonna reduce this a little bit. 10 seemed a little fast if I was playing it back without any like real time toggle on. So I'm just gonna do this times 2. Just seems like it's evaluating a little quicker for me for some reason. So let's do uv.y, and then we're going to set that equal to cosine of at time times 2. If you remember, when you have kind of two hey, Zach, how's it going? Hey, Orient. Glad to have you guys with us on the stream. Thanks for joining. Good, Orient. I'm glad you're able to watch live. That's awesome. All right. So if you remember, when we have 2 different kind of axes of our, in 3 dimensions, and we have them, one working on sine and the other sine working on cosine, but feeding the same value into both functions, we're going to generate a circular path, right? So this is going to start moving him around in a circle. So let's take this, and we're going to set UV, excuse me, equal to a fit function. So we're taking this UV and fitting it, right? And so we know it's going to be going from -1 to 1. And instead of going, -1 to 1, that's not really going to work in our case. We're going to do scale it down a little bit. So we're going to do -0.2, comma, and then do 0.2, just like so. So now we've kind of changed the scale of that. How that sine function is going, sine and cosine functions are going from -1 to 1, making a wave. Now it's just going from -2 to 2. So we've kind of scaled that down. Okay, so then next we're going to add plus equals, and we're going to add in these 2 attributes to it so that we can offset, where this circle is in space, because -2 to +2 actually is going to go outside of this 0 to 1 UV space of our polygon, right? So we need to add, something to it to bring it back in. So we're going to add 0.5 to both, and that should bring us back kind of into spec here. I think the last part there is going to stay the same because we're still using our UV variable and everything's writing the same. All right, so let's do that and let's hit play and see what happens here. And so now we have Flippy kind of rotating around in a circle, and he's not being positioned based on what direction he's moving or anything like that. It's still just calculating that orientation of his, where he is based on the normal, and then it trying to calculate some sort of secondary vector to lock him to. So as it's kind of changing, that kind of frame of reference is moving around, and so it can't always calculate that and have him not rotate around. So there we go. We've got him rotating around here, right? So that's kind of fun, right? That's kind of interesting. But let's look at something maybe even a little bit more different. I'm going to turn this transform off, and we're going to change this grid from a polygon to a NURB surface, right? So just as it is, that's still going to work, right? That's still going to make him go around in a circle like so. But it's actually really weird. I don't know why that's showing up as like grayish like that. But what we're going to do instead is we're going to put a mountain sop down here. So let's do a mountain, which, as I've said many times, is actually just now an attribute noise set to kind of the parameters of that old mountain sop. That old mountain sop sounds like I'm like, I don't know, some old guy or something. All right, so we're going to animate our noise here. And what we're going to do is up the amplitude a little bit here. So what this is going to give us is kind of this like smooth surface. It's a little maybe hard to see here for some reason on the top like this. Just make sure I'm not doing something really dumb. Well, at least that's a little bit easier to see. And let's maybe just do smooth shaded like so. Cool. So we've got our this kind of smooth surface here. And so as we animate it here, we're going to be able to see this kind of surface where he's kind of riding up and down on it like this, right? And so, hopefully you can start to see some more practical examples of how this might work with, with maybe attaching a boat to the surface of an ocean or something like that. So, yeah, so that is kind of the idea of sticking an object to another object using prim UV, right? So basically we're specifying the UV point and we're looking that up, right, from the primitive and attaching, our point to that. Basically, that's what we're doing. So because if we look here, just to remind you, the add point is not moving, it's just dead center. And this is the thing that's moving that point around kind of in 3D space. So there it is moving around based on that. So if we look at our SOP there, it's moving around like so. So, all right, hopefully everything is making sense. Crossfader, I hope I kind of cleared things up for you there. Hopefully this is we're all good kind of moving forward with this. Let me know in the chat if there is something that still isn't super clear, but we'll continue forward and kind of see what the next step is here. So the next thing that we're going to talk about is UVs versus parametric UVs. And what you may have noticed is that we haven't declared any UVs on our grid here, especially in this case, right? This is a NURB surface. It's got some point positions, things like that, but it's not, we don't even, there's just one primitive. We've got some vertices and things like that, but we're really not doing a whole lot as far as UVs. We haven't declared them, right? So what is, exactly going on there? So what we're actually using to look this up, right, when we're talking about prim UV is we're actually talking about the parametric UVs versus our like defined UVs in this case, right? So in this situation, we have a grid, right? So let's add in some UVs and we can take a look at what happens when we actually do that. So we'll just do UV project here. And I'm going to go back to, instead of a NURB, I'm going to go back to a polygon. And I'm going to up this a bit, I don't know, 20 by 20 maybe. I'm going to turn off this mountain. Don't need that. And I'm going to turn on this so we can actually see our UV grid here, right? So we could also use an image or something like that, but let's just take a look at this. Oh, sorry. I don't need to up the resolution here because that's going to screw us up. So let's just do this at 2 by 2 because now we can actually have a conversation here still about it. So, okay, so we've got our UVs there. But as we look here, I'm going to just hit play. And as we look and as we scale these UVs, right, nothing is going to change about how this object is moving around here because it's looking up these parametric UVs of our actual primitives here, right? So we have just one big primitive here, right? So if we look at this here, we just have primitive 0 right there. That's it, just one. So we're actually calculating this parametric UV per primitive, right? It's not a global thing across the whole surface. So that's why if we were to change this grid from 2 to 2 to something like 3 and 3, right? Well, now when we do that, let's come down here, we're going to see that flip is going to be up in this top quadrant here, right? Because it's looking at the 0 primitive, right? So if we turn on our prim numbers again and just come back up here, sorry, we can see that this is primitive 0. So our code here is looking up primitive 0. So it's looking up this kind of parametric UV on just that one primitive, right? So that's kind of a really important thing to notice here. So let's up this grid just kind of back to our standard 10 by 10, like so. I'm going to turn this off. I'm going to turn off that. We don't need that anymore. So now let's do a scatter here, right? And this is going to help us visualize this. So let's do scatter. What we're going to do is we're going to up the total number. So we've got a lot of points here. And there we go. Cool. Good, good, good. This is answering your question. Good. Yeah, we kind of at first actually ignored that by just making it one big primitive because then it sort of makes sense and you can understand what's happening. But then when we add in the parametric, we can talk about each individual primitive, right? And then, so we've got this scatter here and we're going to help visualize the source primitive UV by changing this to CD. And so now what we're actually getting here, in fact, I could probably even up this a bit more. Who cares? That'll be fine. Lots of points. So right now what we're seeing is the actual this parametric UV space for each of the primitives in our grid, right? So it's going from 0 to 1 in each of these individual primitives. So this is a real easy way to kind of visualize this. If we look here, Matt actually did a nice little GIF for us where we can see some of the, yeah, exactly. I'm sure actually if we look in here, yeah, I'm sure that they mention here, yeah, right here. The function specifies the position using intrinsic primitive UVs. So there is another function that will actually just do the UV attribute that's called UV sample. So that's actually a separate function. So something to keep in mind there. But yeah, it seems like you're like, well, why isn't it working with the one way and not the other? So yeah, it is a very specific code, but it's something that's really commonly used. So here's the same point method done on some of the actual primitives like a tube or a sphere, not polygonal, but primitive versions. So we can kind of see how those UV spaces work. The disk one's really interesting because that's like really hard to kind of calculate. So it kind of just goes around radially. Sphere is tough as well. So pretty interesting to see those. So this is, one of the things that he mentions here is that if you've ever done some mantra rendering and just applied a texture to a default grid and wondered why you're getting like a per face UV, that's why. So in the absence of real UVs, the renderers within Houdini, most likely, in fact, I'm assuming Karma would be in the same boat, will just fall back to parametric UVs if you're not actually feeding them actual UV attributes. So something to keep in mind there. All right, well, let's just keep rolling on here and look at XYZ distance. So XYZ distance is a really popular function and super powerful. So the prim UV, gives you the attributes you want if you give it an actual UV location, right, to look it up. But what if you want to get Oh, and minimum position, that was when we talked about way back, gives you the closest position on the geometry, right? So you give it some arbitrary position and it feeds an arbitrary, it feeds the minimum, point on the surface. Prim UV can look up an attribute on a surface, but you need to tell it where. So if we want to take those two ideas and bridge them together, right? So we have a position in 3D space. We want to get an attribute from the closest position on a geometry. That's XYZ distance. So that's the idea that we're dealing with there. We have a point, we have a surface, and we want to get an attribute from that surface in just one step, basically. So anyways, this will make sense a little bit more in a second. So I'm just going to get rid of this scatter. We don't need that right now. We still have our add. And I'm just going to disconnect most of this other stuff here. Let me just zoom in here so you can kind of see what I'm doing. No problem, Crossfader. Yeah, thanks for joining us. All right, so we're not going to be doing this right now, I don't think. Well, we'll leave it as it is, but we're not going to be doing these, so I can probably get rid of those. All right. So let's just cut these, and we're just going to work with this section here. Shift L will arrange our nodes nicely, and let's just scale this down so we've got it down here. Great. Okay, so let's set up this XYZ distance and get some attributes from it. So we've got our grid here. Let's do just like a flat shaded so we can see. And then we have this add point here, and I'm just going to highlight this so we can see, okay, we've got 1 point there. I'm just going to raise it up and kind of arbitrarily move it along, just like that. Cool. All right, so let's reset this, middle click, control middle click, and then we're gonna delete our spare parameters. All good. All right, so let's set I at, oops, don't need a space there, prim ID. So we're just gonna kind of initialize these, V at UV and at dist, which is just gonna be a float. So let's say at dist equals, and we're going to say XYZ dist. So we're going to look at the second, geometry, the second input geometry by using 1. We're going to look it up based on the current point position that we're, iterating over. And then we're going to put in prim ID here and at UV, like so. We're going to hit enter. So we have our grid. Actually, don't even need this UV project anymore. So we've got our grid, we've got a point. And so what we can see here is that this is actually going to return us 2 values, or technically 3 values, right? We're getting distance, UV, and prim ID, and we only set distance equal to something. So clearly there's something else happening here. But let's just look at what's going on here with our data. So I'm going to pin this so we can keep that there. And I'm going to click back up here and make sure, if you didn't hit enter, and that'll bring up these handles to be able to move around. So as we move around here, we're going to see that the primitive ID down here is changing, right? Also the UV number and the distance is changing. So the distance should stay about the same because we're not moving closer or further. But if we moved in this axis here, we could change the distance, and we're just going to be changing the, the second UV coordinate there, and not the first UV coordinate. So the whatever primitive we're looking up is going to change, the distance is going to change, and we're going to have some UV change as well. So, okay, this is all really interesting, but how in the world is this happening, right? Because we've, again, in our code, we've only declared one thing we're only setting one thing equal to. And this XYZ distance is one of these really interesting functions that allow you to actually save multiple things in one function. So this is a really powerful function to use. So again, I'm just going to bring up F1 here, let it read this. And so now what we can see here is that when you look up functions in Houdini in the help documentation, and you see these little ands, right? What that is going to actually indicate to you is that those values can get returned as attributes, right? Or as variables, whatever you might want to use them as, but you can actually get information from that. So in this case, what we're saying is that we're getting our distance here, right? Which is a float. So we're setting, right here, we're setting distance, right? So that's a float attribute that we're getting. So here it says float, but we're giving it a geometry, giving it position, right? And then, so this geometry is the one we're looking it up to, like the surface we're looking to. The origin is the position we're looking from. It's getting the closest distance between those, right? And then here it's going to return the prim number number and the UV attribute. So that's what we're getting right here. That's how we're setting prim ID and UV. So those are actually being returned to us and we're not setting that in the function. So it's a little bit of a different way to go, but when you look up your help documentation, you'll see those little ampersands there, and that'll give you an indication like, oh, this is different. This isn't going to work the exact same. And in fact, you can see right here that we can actually add another value at the end as well. But for right now, we're just going to be using it this way, and this is something to just keep in mind that this is what we can do, right? So, okay, great. We've got this distance that we're calculating between the point and the surface. We're returning the closest prim ID and the closest UV coordinates. So now we can kind of do what we were doing before with prim UV, but now we know a lot more information just from this one little calculation. We can add a line here that says at P equals, and we'll do prim UV, and we're going to go look up the first or the second input, right? And the position here. Then we're going to feed it in at prim ID and at UV, which we just looked up here. So we're going to feed those back in to be able to look up the position on this surface that we just kind of found was the closest position, right? So if we hit enter now, that is going to kind of link those. It's going to snap it to the surface now. So now we can look up this position, and it's actually snapping to the surface. It's getting this closest position. It's feeding back the prim ID. So it's doing a whole lot in one little block of code. I'm going to lock this down as well, just so we can remember what's going on here. So this is really interesting, right? So we can do that. But the one thing that's really different about prim UV versus like min pos, which we did before, is that it's not just going to give you the closest position. We can query any attribute from this, right? So now what we can do is we can actually use this to get something like color. So I'm going to do an adjust color. This gives us a little more control over what's, the color values that we're going to set up here. So I'm going to unpin this now, unpin that. So let's just do like 100 by 100 so we can get some interesting colors here, a little bit more. This is basically what Matt did here, but I'm just kind of going a little bit further with it. So we're going to do a noise to look it up, like that, and then we're going to scale this just a little bit so we can have a little bit smoother noise. So now we've got this point, and instead of just having just seeing the point position, let's take this copy to points here, and we'll wire it back in. And instead of our rubber toy geometry, we can get rid of this, and let's just grab a sphere. Sorry, it's a little zoomed out, but there we go. So we've got a sphere there. We're using sphere and copy to points. And we can merge this back in. So we've got kind of everything all together. So we're going to grab our grid there. Cool. So now I'm actually going to set this, instead of polygon, I'm going to set it as a primitive. So it's just 1 point, right? So what we're going to do is we're going to use this to, instead of just getting the position of this, point on the grid, right? Snapping it to the closest point on the grid, because we're up in the air now, right? So we're snapping it down to the grid. So instead of just doing that, let's now have it read the color. So we're just going to add one line here. I'm going to say at CD equals prim UV. And this is actually going to be almost the exact same thing as above. So I'm just going to copy this because there's no reason to waste too much of our time here. We'll just do CD in that and make sure there's a semicolon at the end. So now this is going to look up the closest position. It's going to get the attributes from these primitives here in this grid. It's going to tell us which specific primitive we're looking up and what UV is the closest, right? So these are all things that it's gathering from this first closest distance calculation. And then we're just reading attributes using prim UV. So now as we move this along, it's reading both the nearest position and whatever color was at that nearest position. So it's pretty cool, pretty powerful way to be able to kind of link a whole bunch of different things together, right? In fact, Henry Foster, who is the guy that has done MOPS, he goes into a bunch of detail on his blog from what Matt says. So I'm just going to post these in chat here for both of our chats that I've got running today, unfortunately. So there we go. We've got a link to his blog where he talks about this in a pretty good amount of detail. There's also a way to not have to do all this vex, and you could use an attribute interpolate SOP instead. That's what Matt's talking about here. But so it's very similar to the idea shown here. It's looking for, it's trying to get, have your points with the source primitive that they're looking up, and also the source primitive UV that they should be looking up from. So it's going to be doing the same thing in a SOP level. So it's something to keep in mind there. But let's see here. This is the attribute interpolate SOP. So we just basically get two geometries here. One's the destination, one's the source for the attributes to interpolate. And it's basically looking for source prim and source prim UV. So you could certainly use some of these, you could use some of the ideas here plus this SOP and be able to do some of those things as well. So, and the interesting thing here is that this is able to look up point attributes, vertex attributes, a whole bunch of different stuff. So it's maybe, this could be a little bit more of a concise way of doing it, depending on what you're doing. It's just something to keep in mind, right? So that is day 19 of the Joy of Vex. I think hopefully we've kind of cleared up any confusion that might have been, in our understanding there. But if you have any questions, drop them in chat. I'd love to be able to at least touch on them to make sure that we're all clear moving forward. And I'm going to go over some of these exercises, maybe just to talk through things that you might want to do on your own to kind of expand your knowledge. So one thing that you might want to do is use modulo with time to animate the UV vector you feed into prim UV. So what that would do is have, basically you would modulo your time, and that's, if you remember, that's like the having a kind of loop snap back from 0 to 1, right? So you could have it slide across your grid and then maybe snap back to the beginning and then snap back to the beginning using a modulo like that. So the next one is finding an example on the cgwiki of using the attribute interpolate with a scatter SOP and see how it's similar to the prim UV trick. So that'll actually walk you through a little bit of how that node works, the one that's right here, the attribute interpolate. So try prim UV with curves and polylines. See if you can push points along a curve. So if you had a curve, how would you look up, where the closest point in that curve is, right? It's still a primitive, so how would that work? So that's one thing to think about. So using the same thing above, how would you get cars to properly orient themselves on the curve? He says the lazy way is to use the trail SOP, set it to calculate the velocity. And if there's no other normal, up, or orient attributes, the point will get copied along the velocity. But then how would you convert the velocity to an orient so it has a stable rotation? So remember, we only have one vector, right? So we needed to keep a stable orientation, because if we're giving it one vector in one direction, Houdini can still kind of try to figure out what this other rotation is. So we need to give it a secondary vector so that it stays locked in place. And then see if you can replicate some of the workflows we did here with an attribute interpolate SOP. Some work, some don't, but and there's obviously things that might work with an attribute interpolate that wouldn't work with this code here. So anyways, these are some exercises to kind of increase your knowledge of Vex and of what we're doing here, these concepts. All right. Well, I'm feeling good. I don't see any questions in chat, so we're going to continue along. And we did it, guys. We're at day 20. So if you followed along this whole way, we're at day 20 of the Joy of Vex. So hopefully that's exciting for you. And we got one more day's worth of content to go through. So let's take a look at this. And this one's a really interesting one, I think, because it's kind of a different concept and is a little bit more of a niche thing, but it's super powerful. So definitely something to keep in mind here. So let's take this. I'm just going to make a copy of it, and then I'm going to get rid of some of these things that I think we're going to keep this add. I'm going to get the color out of here, interpolate this one. We'll keep the sphere around in case we need it. This I'm just going to slide over. Just going to kind of reorganize a little bit here Don't think we'll need those for a little bit. And looking good. All right. So there we go. We've got Joy of Vex day 20. I am going to move this up here so we can see it. And let's just reset this, control middle click, and we don't have any spare parameters, so we're good. All right, so we've got our point here, right? So let's move this back, and I'm just gonna set this back to like the grid position so it's sitting on the grid here. All right. So we were talking about kind of minimum position, this min pos function. So let's talk about point clouds. That's where we're going here. So we're talking about min pos as being kind of the simple solution of trying to figure out the minimum the minimum distance to a surface and like where that is on the surface, right? And prim UV and XYZ dist are kind of the versatile versions of the same thing, right? Because we can get any attribute we want, just not just the position. So near point and near points, those two where we're looking up points that are near maybe some arbitrary point that we're feeding in, those are the simple version, and the more advanced version of that is the point cloud functions. There's quite a few functions, but they're all grouped by PC, I believe, is kind of the prefix that we give them. So PC, whatever. So we'll talk about that in a second. But first, we're going to talk about how we would do this using the simple function, which is the near points, right? So let's set up this. And what we're going to do is we're going to use a 10 by 10 grid, just like we were before. So let's do this 10 by 10. And we're going to set that into the second input here. We're going to look up the nearest group of points to this add point that's coming in here. So whatever nearest points are to this, and then create them, right? So right now we only have one point coming in just like this, right? There's our 1 point, but we want to actually find the closest points on this grid and add those points in as well. So we're going to do that here. All right. So let's set up a variable called points. So this is going to be a point array. It's going to be an integer array, of indices. And we're going to set that equal to near points, right? This is going to give us an array, and we're going to look up the first geometry using the current position. We're going to give it a distance using a channel D. So this is going to be kind of the distance we're looking within. And then the number of points to look up is going to be 25. Just in this case, we're just going to set it at a maximum. Cool. All right, so that's going to give us our all these points that are close by. So then we're going to also declare int pt because we're going to use that in a for each loop soon, and we're also going to declare vector pos for position. Okay, cool. So we've got some declared things. So now we're going to do a for each, right? And we're going to say for each point in the points array, like so, right? So this is the array we're looking over here, and we're gonna each time we loop through this, we're gonna change the value of pt, right? So here's our brackets that we're gonna work inside of, and now we tab in, and we have this is what we're gonna be working on here. So we're gonna set pos, which is gonna be a vector. So we're gonna use the point function to look up whatever's coming in on our first input or our second input here. We're going to get the position of that, right? So this is, this is the position of whatever current point we're iterating over, right? Because we're going to have an array of point indices. So we're going to use those to kind of iterate over that array. So there's that, 0.1. Yep. And then what we're going to do is for each of those positions, we're going to add a point. So we're going to use the add point function. We're going to set that to geometry 0, and we're going to use the position we just looked up from the grid to create points there. Great. So we need to add this channel parameter. And now as we slide this up, we're going to see, oh, it just found 1 point that's close to it. So it's added that into this geometry. So now we have 2 points there. And as we slide this up, we're going to get more and more points near it. So these are all the points that are within 2.8 units of this original point here. So as we take this, slide it around, you're going to see that it's going to be finding more and more points around it. And this is a way that you could, look up attributes from those points, do whatever, right? But it's finding those points and feeding those into our for each loop, because they're getting those points from this second input here are all getting stored in this array, right? just for an example, if we, just to remind you, if we do an attribute of our own, we're going to do I at A, just like that. And if we set that equal to points, right, we can actually see this array, and I don't need to put those there. Sorry, my bad. So here we're going to see all of these nearest points, right? And the reason that only 0 is getting this is because that's the point we're running over. All the rest of these are being created by this vex code. So if I bring this all the way down, there we go. We don't get any. Now we have 1 point in the array, and so therefore it creates 1 more point. So this hopefully kind of clarifies a little bit of what's going on here. Like as we slide this up, we should get more and more points in that array, and therefore more and more points will be created, right? Because we're looking up the nearby ones. So let's do this. Since this is what we were saying is basically the simple function of the simple way of doing this, let's look at the more complicated way of doing this, right? Let's use the PC find. That is the way of doing it. So this is like point cloud PC find. So we're finding things in the point cloud. So, all right, so let's just change this up a little bit here. So instead of near points, really the only thing we need to change here is PC find, right? You can see there's other things here. We're going to be looking at the geometry coming in on the second input. We want to return, we want to look up the position of those. So that's the only thing we have to change here. We have to say we're looking up the P value, the position attribute there. And we want to go from the current position here. So now we have, now we're basically storing those into this point cloud, right? And what we're doing here is going to be storing it in an array here, right? So that's all well and good. This should give us basically the exact same thing, right? Because we're doing the same thing. We're using the same distance. It's finding the same points, all that kind of stuff. And as we change this here, you know, whatever. So in a simple case like this, this is going to be basically identical. But one of the cool things that we can do with point clouds is like filter and average and do things with this grouping of points that we've created. So it's like an optimized way of being able to calculate some of these things without having to do quite as much code. So let's do this next example. And this is going to give us a good idea for how we can optimize our code by using things like point clouds. So this next one's going to take a second. So we're just going to set this up and then we'll get into the code. So let's grab our geometry here. Let's just do that. Let's do a circle, right? We need a circle. Create a circle. And yes, that is good. We're going to set this circle to be on the, turn that off. We're going to set this to be on the, oh, this is pinned, that's why. We're going to do it on the YZ plane, and we've got our geometry here. So we just want to get this circle basically set to the same size. So we're just going to scale this up a little bit, move it a little bit like that, maybe scale it down just a little bit. Great. And Matt suggested about 50 points, so we'll do that. We got 50 points here around the circle. And let's make sure that it rotates slowly on the x-axis. So we will do that, and we'll say rotate, say at time multiplied by 3. So now what we have here is this kind of slowly rotating on the x-axis, right? Cool. All good so far. So we're going to set this circle to the first input of our point angle and this to the second, just like so. All right, so let's start to clear this back, delete the spare parameters, and we're good. Oh, you know what? I want to do this as not a closed, but an open arc as such. Cool. All right. So the first thing we're going to do is we're going to snap the points on the circle to the closest points on the toy. We did that with minimum position, min pos. So we're going to do that in this case first. So let's set our function here as at p equals min pos. We're going to look at the second input and use the current point position that we're iterating over. So let's hit enter, and there we go. Now it's snapped to our geometry. And as we play this, we're going to see that those points are going to, be rotating around, right? They're rotating around like this. And so they're snapping how they're finding that closest point as they kind of rotate around our geometry, right? So we're seeing it like this, kind of moving along the surface. But really what it's doing is finding the minimum, the closest, position on this toy. It's actually kind of just snapping to this closest position and not not really smoothly moving over the surface, right? So let's kind of try to smooth this out a little bit. So what we're going to do instead of just doing min pos, we're going to use our near points again. So let's do this. We're going to change this to another int array called points. This is going to be basically the same thing, equal to near points. And then we're going to use the second geometry, the position, right? We're going to again set up a distance slider in order to look things up like that. And then we're going to give it an integer channel called amount, basically abbreviation for amount. And that's going to say how many points we're actually looking up. So that's good. We're then going to declare a point integer, a vector position, which is just going to be equal to 0. That's going to set all of the components of that vector to 0 just by giving it one float like that. So then we're going to do the for each again, for each, and similarly we're going to do points like this. And let's do our curly brackets. And what we're going to do in here is we're going to take the position and we're going to add the position in from this point, whatever point that we're currently looping over. So we're going to add all these point positions together. And then at the end, we're going to do one more step and that'll cause it to average. So here we're going to get the position from the second input over the current point that we're iterating through in the for each loop. And then at the bottom here, we're just going to say at p is equal to pos, which we've been looping over here and kind of adding together those vectors, divided by the length, the number of points in the array. And so that's just how we do an average, right? We take all these values. So maybe there's 10 values, right? We add them all together and then divide them by the number of values, right? So that's how you get an average. And this should evaluate like so. We need these attributes here. So we need it to work over a certain number of points. So we'll do maybe 10 points. And then we'll give it a certain distance here that it needs to operate over. So let's say the D is 10 in this case, and the amount is 10. So as we hit play, it's going to be a bit smoother, not quite so smooth, but as we up this, right, this is going to become smoother and smoother because it's going to be able to slowly kind of average across multiple points that it's looking up on the surface, right? So let's say we got up to 500, it's going to get really smooth, and then 1,000 is going to get even smoother, right? The only thing to keep in mind here that's happening is that when we're averaging, we're smoothing not only how they're moving across the surface, but also the shape. They can't move as closely linked to the surface because we're actually averaging all of the points on the surface that they're looking up. So that's kind of what we're doing here. We're looking up tons of points on the surface and then finding the average of them and kind of moving these along. So that's why it can move smoother, but also why it's adhering to the actual shape of the geometry less and less. So just something to keep in mind. However, all of that we just did here, we can do with just two lines of code with point clouds. So let's take a look at how this works. So instead of this, let's do int, or you know what? I'm just going to do this. I'm going to leave this as it is, and I'm just going to do control// to comment those out. And now I'm just going to go down and start a new line here because we're going to use these same sliders and all that kind of stuff. So let's do int my PC. So we're creating a my PC integer, not an array, an integer. So in this case, we're going to say PC open. We're going to look at the second input. So this is a different function. This is PC open. And so we're going to set 1. And we're going to use P. that's what we're going to look up. Then we're going to look up from the current point position, and we're going to again use this distance to give us a distance to look within, and then CHI, AM, and T. That's the amount of points that we're going to look up. So kind of a limiting factor of how many points we can look up. Cool. So that's going to open up this. It sets up our point cloud, and so this is like this gives us this first number here gives us this temporary thing that we've created, right? Usually we use 0 to say the current geometry we're working on. Now we have this point cloud 1, and that's going to be, this is going to refer to a thing. So this is a little bit different than the way we would normally, do our, work with something like an input, right? It's a little bit different. We're actually going to be creating a thing. That's going to be stored in 1. Sometimes we have things that are stored in 0, like when we add points and things like that, that's on 0. This case, we're doing it on 1, which is a little bit different. So just keep that in mind. The second line is we're going to use one of these other functions called PC filter. So we're going to say at P equals PC filter. And this is going to take my PC and the P attribute in there. So this is basically going to do the sum and average trick that we just did with the other, with the last bit of code. And it's going to give us basically the exact same thing, except in 2 lines of code, right? So this is going to be doing a filter on it, giving us a very similar situation with a lot less code, right? So we can do that, but we can also get really any attribute from the point cloud, right? We don't have to just return P from the point cloud, right? Because in this case, we've put this stuff into this my PC, and here we're reading an attribute from it. In this case, we're looking up between the position here and the position there, right? Now we're reading back the position. But what we can do here is we can read back any attribute, right? So we could change this to be N, and then, here we'll set this to N. And then the next one we're going to set equal to N equals normalize, of our N. And we're going to multiply that by 2 just to make the vectors a little longer, easier to see. Cool. So now this isn't actually moving it, but it's adjusting the normals. And the way that we can see that is by obviously turning the normals on, right? So let's start this back where we were before. We can see now we're returning the average normal between all of the points, the nearest points on the geometry, right? So that is a really interesting thing to see, right? We could do something and pull this down a little bit more, and they're going to be even snappier, right? Kind of like they were at the beginning. Or we can go way further, and they're going to be a lot smoother as they kind of slowly go around this geometry, right? So this is hopefully starting to show a little bit of the benefit of using this point cloud idea, because what we can do is we can read all, get all these near points, put them into this point cloud, and then we can start to run functions on that. Here we can see this is my PC. This is this point cloud that we've kind of stored in this integer, right? And we can then pull out attributes from it, like N. If there was color on it, we could also pull color out, for example. So let's now do that. Let's pull out color instead. So let's use this right here. We'll set up this grid. We'll pull this over instead. And, or actually, you know what? We can just take this grid. We'll just split these off and we'll feed that into there. I'm going to untemplate this. Turn the points off. And here we're going to set this to be 200 by 200. So it's really high resolution grid so we can see some colors on it, right? And let's see. Attribute from map. That's right. So we want to use attribute from map. It's going to give us this grid pattern here. So we'll just kind of rotate this so we can see it. Now it's backwards, obviously, but that's not going to be a huge issue. Let's just reset that. Actually, no, we don't even need to. We can just leave this kind of as is, and we'll just slightly change it. So we'll say int PC equals PC open. And instead of looking at the second input, we're going to look at the first input here. And this is going to store the information into this PC, right? And so we're going to look between P and so we're going to look between the position on the grid and the current point position, right? So in this case, we're doing it just on its same its original point, so it's really not looking up from any separate point position. We're going to use the distance and the amount of the number of points around it. Here we can say, then we can just do CD, and we can get rid of this. So here we're going to change this to CD, and we're going to do the same kind of averaging function on it, but instead we're going to change this to PC because that's the name of our point cloud up there. And here we're going to do the averaging on CD. And so now, let me turn off the normals. What we can actually do with this is we can change the number of points that it looks up. So if we just do 1, it's just going to return the same point color, right? This should be the same. But as we turn up the number of points, it's going to get blurrier and blurrier because it's taking all those points around it and averaging them together, which is then going to blur. Obviously, if we go too crazy with it, it's going to get real slow, but an interesting thing to do. You can also use an attribute blur stop, which is going to be much more handy probably and easier to set up than doing all this code, but it's something cool to see nonetheless. All right, so what if we used a lookup? Here we're looking up using P, but what if we used the lookup from something else other than P? I'm just going to clean that up a little. So let's change this and do something maybe a little more interesting. So instead of this attribute from map just being this UV color, let's change this to be, where's the name of it? Mandrel.pick. There's a bunch of things that we can use by default in Houdini that are kind of default mapped into attributes. This is one, it's just a picture of a monkey basically. But okay, so we're going to use this mandrel and we'll come down to our code here. Right now it's blurring, but we want to change this. Let's tweak this a little bit. So it's blurring here. Let's change this to have a scatter as well because we want this to be a bunch of points. So we're going to color all these points. Let's do this. Let's do D and change the geometry size of our points. Let's do this to like 6 so we can see it a little bit better. There we go. And let's up the number of points. There we go. We got 10,000 now. Cool. All right. So down to our code to now work on this. Right now it's blurring and that's really not what we want to do. I mean, it's still interesting. It can blur even though they're on points, right? It's kind of neat to see. But let's change what we're looking this up based on. So instead of P, let's look up CD based on the current CD. Same thing with distance and the amount of points that we're going to bring in. Here I'm just going to set this to 1. Distance 10, fine. And now here at this, let's not change the CD, but let's change the position. So now we're going to filter the position of this point cloud, right? All right, so now let's see what happens. So as we up this amount, we're going to see, oh, I got to go down here, right? These are actually going to now start to cluster because we've averaged the position based on the nearest color. As we up the number, it's going to put them into these kind of average positions based on what's in the closest color, right? So it's a really interesting kind of way to go about this, right? So we could do, let's do like 500 there. And then we could also use this to say how far it can look up, whatever. But we'll just leave this at 10. So you can see that these are going to kind of slowly coalesce into these sections based on their color, right? So the red is kind of grouping, blue is grouping there. This is kind of this swath of this greenish brown. So it's almost like turning it into a like a color space representation, right? Based on the point color. So sort of interesting thing happening there, but let's do the same thing, but just to show that we can do this on other attributes, let's do it based on normals, right? Let's look it up based on similar normals. So let's take our pig geometry. We'll take this here. We'll swap it out for our grid. Yeah, you're angry at me, I know. Let's also make sure that there's normals on this, point normals. So let's do normal here. Change it from vertices to points. Great. And let's subdivide this too, just to make sure it's nice and smooth. So we'll do this 2 subdivisions, sure. And we've got our scatter here. We don't need to have this attribute from map anymore. that's fine. Now we've got our point positions for our pig. And let's take a look here. So what we're going to do is we're going to, instead of using CD, we're going to use N and look up based on the normals. We can use the same distance here. He changed the name there, but we're just going to keep it this way so we don't have to redo all of our code. So the P is going to be equal to the point cloud. It's going to filter the position here. And then what we're going to do is we're going to write the at CD based on the normal. So we're basically going to write the normal into the color, right? So what we're going to get here is if we go back to 1, we're basically back to this pig and it's like normal shaded, right? And it's going to now group them based on their kind of average normals, right? So it's going to move them all based on where their normals are averaged to, right? So now it's all grouping them based on their normal positions. Now we're visualizing that with color, but just know that that color is based on the normals, right? Uh-oh. All right, well, it looks like my stream went down, which is really unfortunate, but we will keep going. And I will set this back up later here. Let's just do this. Oh, that's really unfortunate. Well, we're going to post this live anyways, and you'll be able to see this after the fact. So my apologies for this going down. Hopefully you guys will be able to reconnect and come back in, but this will be on YouTube as well. I'll make sure that this is posted. All right. So we're doing that by N. Cool. Last couple things here are just going to be some examples, some example files that we've downloaded. So I'm going to load those up real quick. Let me just close this here. And I'm going to grab those from my folder and we'll start working on those. Well, welcome back, everybody. If you lost us there for a second, my apologies. Glad to have you back, though. All right, so the first one we're going to look at is this pop force. So these are going to be a couple examples, more real-world examples of things that you could use for these. So I'm pretty amazed that in how many weeks of doing this, I've not had any internet issues. That's my first one. Anyways, guess Saturday's a little bit of a busier day for the internet in my area. Anyways, my apologies if you missed out on this stuff. Sorry about that. All right. Here is a real world example, and we're going to talk a little bit about how this works. So here we have a tube. All right, so we've got a tube. We're using a point wrangle here to set some noise into a position, right? So we're setting up just a bunch of different things to kind of drive the noise. This is going to change it based on the Y position, scaling it based on that, adding a time function into it as well, and then multiplying that by 3, and then multiplying that by this vector here in order to make sure it's only going in and out and not up and down, right? So that's keeping our noise scaled to just the X and Z axes. Then we're setting the position to this p.x times pos, p.y, and p.z times pos. So we're multiplying these two by pos and leaving this as is. So that'll stay just as it is. If you guys missed anything from if you're coming back and you'd missed anything, we will be putting this, I'll be reposting this on YouTube, and you'll have this full video to take a look at. My recording is fine on my end, so we should be good there. Okay, so we've got a tube. Here we're doing a polyframe, which is just basically giving us a velocity to work from. And in this case, it's just a tiny little velocity vector that is pointing around this. It might be a little hard to see, but there it is right there, pointing in that direction. And then we're adding some lift to V, basically. So we're adding a vector. If we scroll down here, this is basically just adding 6 into that. So it's kind of lifting this vector up. And basically, in this case, V is showing the trail direction. So it's actually, the vector is pointing this way up and to the right, even though it looks like it's pointing down and to the left. So what we're going to do is feed this into a pop network. It's going to try to calculate everything right now. Cool. Let's jump in here. And fun fact, there's pop wrangle too. So we can actually use this inside to mess with particles, right? So here we're going to actually be using the PC open to find the, the nearest, points within 10 units up to 30 points, right? So let's just play this and we'll see what happens, right? All these are going to swirl around and start to go up, right? So in this case, our input is going to be the second context geometry. So if we come back up here, this is the input that we're reading from. Right now, the grid is what we're sourcing from. So we're sourcing from the grid and getting the, and pulling information from this second input here. So this pop wrangle, we set these inputs right here. All right, so the vector, we're getting, we're filtering the velocity. So this is the average velocity from that, the average position from that, and then multiplying those times some scales. In this case, we're going to be multiplying, we're scaling the velocity up by 0.1, the position that it's moving kind of averaging up by 0.1, so it's not moving maybe as quickly. And then we're setting the velocity equal to average velocity minus the average position. So this is basically blurring the velocity and the position from the cylinder and then calculating velocity from that, right? So we have kind of this smooth velocity force, and it kind of forces all of these points to kind of come together, right? So let me just set this to darker background here. Maybe gray will be good. And we'll just kind of look at what this is doing here. So it's going to take these points coming up off of this and kind of slowly averaging them to that cylinder as they go up, right? So it's smoothing, averaging, and doing all of those things, from themselves, right? So kind of interesting there. Now, what we can do instead of instancing them from this ground geometry is we could instance those points directly from this first. So we're actually going to source from that first geometry and then also do all of our point clouds from our first geometry as well. So now what's going to happen here is as these come out, they're going to start to clump together in a really interesting way. And so we can up the number of points here that we're going to be looking across. So maybe like 100, right? Instead, it's going to slow it down. But what we're going to be able to do is what this is going to do is actually now clump those points together because they're all kind of they're all starting with the same position and all kind of moving in the same velocity. So it's averaging their positions and velocities kind of as they go along. So they're all kind of slowly coalescing into these like spiral arm kind of shapes like this. So it's kind of an interesting thing to do as well here, where you could average these together and get these kind of clumping, actions from particles in this case. So that's one example of something that you could do with it, right? You can download these from the from cgwiki and take a look at them yourself. Also, another option here, let me pull this one open, is going to be kind of a fake ambient occlusion. So let's take a look at this. And so what's going to happen here is we're going to take whatever geometry we're looking at here. I'm going to turn off the this grid so we're not looking at that. All right, so, and let's just use not the flat, we'll just do the smooth shaded version. And let's change our background as well to maybe be gray. Cool. All right, so what we're doing here is we're going to look up a blurred position, a blurred normal via the point cloud, and then get this kind of pseudo ambient occlusion by comparing the dot product of the real normal and the blurred normal. or the distance from the real position to the blurred position. It kind of ends up being a little bit more of like a curvature map, but still gives an idea of some of what you could do here. So we're setting up some, here's our point cloud. We're using, we're looking up P based on position plus normal times a bias, right? So this is going to be our lookup value. So we can kind of adjust how we want those to be looked up based on this bias right here. So in this case, the normal times the bias plus the n. So in this case, it's not, I don't think, really adding in any normal to look it up by, but we can change how much normal we're kind of adding in there. And then max distance and the number of points, just like we have been before. That's all good. We're kind of declaring a few vectors and floats here. So this point cloud position is just going to be averaging the position. Point cloud normal is going to be doing this kind of averaged normal. Then we're going to calculate a dot product based on the actual n and this averaged n, and then a distance based on the position and the point cloud is this averaged point cloud position. So now we have a dot product and a distance. Then we can put the dot product through a ramp to be able to control it a little bit. So down here, this dot CC is going to be controlling how the dot product is kind of being calculated and kind of refit. And then the distance calculation is going to go into a ramp here and get its own controls here. So we just got a little bit of like a kind of fall off at the very beginning of that ramp. And then we're doing at CD is equal to the dot. We could also change this here to say at CD is equal to the distance. So there's the distance right there. So you can kind of see either or there. So there's our distance calculation. And if we swap these around, there's this is going to be our dot product calculation of it. So in this case, if we change these, we're going to be able to kind of increase the contrast there. If we brought this up, it's going to kind of bring up the low value here. So now it's more of a gray low value. We could also make it way more white, kind of increase the contrast overall, something like that. So this is sort of a fake AO type calculation, right? Another thing that Matt mentioned here is he got one of the Patreons gave him a little feedback and said that they would use an absolute function to avoid our dot product returning a negative value. And so they did it on Crag, but we could use this calculation here to get a little bit of a different version of this same AO. So what we could do is we could do this, and I'm just going to copy this in there so we don't have to write all this out, but we'll just copy and paste that in. And so what we've got here, let's just set this up a little bit, and those are looking good. Cool. So we've got our max distance, all this kind of stuff here. And what we can do is set this gamma. And this is going to be kind of our multiplier for this version of it as well. And what's going on here is, let's just look at this and we'll kind of go through the code, right? So we're calculating our point cloud based on the difference between P and P right here. So we're looking it up based on the position. Then we're normalizing this this average n, right? So we're making sure that stays at a unit vector. So there's our point cloud normal. Then we're making sure that our normals are set as well. So we have a vector normal. Then we're getting a dot product between the two of those, fitting that dot product between -1 and 1 to 0 and 1, and then giving a power calculation here. So, raising it to a certain power based on that gamma. So that is just kind of a little bit of a different way of doing this same attribute here. So if we go up to maybe like 2 or something like that, we can see that there. And these aren't even connected in anymore. That's right. So that does not do anything. So that right there will actually conclude the Joy of Vex. My apologies to the folks watching live that we had a little hiccup there in the connection. Hopefully you were all able to reconnect possibly. If not, we will definitely I'll be posting this to my YouTube channel. So I will post on the Discord and on Twitter and stuff, like where and when those came up when it's live. But that is day 20 of the Joy of Vex. So I just want to say that there aren't actually any exercises in here. So we're not really going to touch on that, but there are some more information down at the bottom here. So just take a look at this, and you can kind of maybe now take a look at the Vex page, and maybe you'll feel a little more comfortable going through those actual parts of, maybe more in-depth Vex code and things like that. But the other thing, there's also these great external links. One that I've definitely seen is Entagma's stuff. And so anything that they put out is going to be absolutely incredible. So take a look at them. Think about being, subscribing as a Patreon for them. And then lastly, I've kind of mentioned this a few times throughout the whole series, is Matt's website here, the cgwiki. He has a PayPal and a Patreon link down here at the bottom. Think about, if you've gone through this whole series and it's been super helpful for you, maybe give him a little coffee money, or become a Patreon of his. I'm sure he appreciates it. Super, it's a great thing for him, and gives him some financial feedback to kind of keep the website rolling and all that kind of stuff. So please make sure, if this has been a helpful series for you, that you give him a little green in his pocket. But for me, that is going to end our series on the Joy of Vex. Thank you guys so much for watching. Thank you for being part of the stream today, even though we had some technical issues. And just really look forward to chatting with you guys in the Discord server. And if you guys ever have any questions or anything about Houdini that you want to drop in there, please feel free to do so. But that's going to be it for me for today. Thank you again for joining, and I will see you guys next time. Bye.